All right, today we're doing something pretty cool. We're going to peek inside the mind of an AI to see if a machine can actually learn to spot one of the most devastating diseases out there, maybe even before we can.
So that's the big question, right? And we're going to explore it by following a real project, this thing called NeuroLens. We're going to break down the whole process, how they built it, how they taught it, and the part everyone wants to know. Does it actually work?
Okay, so first things first. Before we can even get into the AI, we've got to understand the problem it's trying to tackle. And believe me, it's a huge one.
You see, the real challenge with Alzheimer's is that by the time you can see the symptoms, the disease has already taken a pretty strong hold. So the goal here, and this is super important, isn't about replacing doctors. No way. It's about giving them a new kind of superpower, a tool that could help them see the invisible, those super subtle signs of the disease way earlier than we can now.
So how in the world do you even start to build an AI brain? Well, it really boils down to two key ingredients. You need stuff to learn from, that's your data, and you need the thing that does the learning, that's your model.
Okay, let's talk about ingredient number one, the data. The team got their hands on a public data set of, get this, 5,120 MRI scans. And these weren't just random scans. They came from real patients at all different stages of Alzheimer's, from completely healthy all the way to moderately affected.
But, and this is a huge but, here's where we hit our first major snag. The data is what we call imbalanced, and I mean heavily imbalanced. Just look at the very mild stage, only 49 scans. That's it. Now, this isn't just a tiny hiccup. This is one of the biggest, most classic problems in all of machine learning. The analogy of teaching an AI to spot a rare bird when you've only got a couple of photos, but you've got thousands of pictures of pigeons, that is exactly what's happening here.
All right, so on to ingredient number two, the actual brain of the operation. It's called a convolutional neural network, or a CNN for short. Now, just think of a CNN as an AI that's built from the ground up to see. It's fantastic at finding patterns in images. It starts small, learning to spot things like edges and textures, and then it starts putting those pieces together to recognize much more complex stuff, like, say, the incredibly tiny changes in a brain scan that might signal disease.
Okay, so we've got our data, our textbooks, if you will, and we've got our brain, our student. Now comes the really critical part, the training. This is where the magic and the hard work really happens.
The best way to think about it is like a student cramming for a massive exam. The AI gets shown a scan, a digital flashcard, and it's told, hey, this one is mild dementia. Then it sees another one. Okay, this one's healthy. And it just does this over and over and over again, thousands of times. With each one, it makes these tiny little adjustments inside its own network, trying to get better and better at matching the scan to the right label.
And it's not just a simple one-and-done process. There's more to it. First, they do something called data augmentation. Basically, they take the existing images and they flip them, they rotate them, they zoom in, anything to create more examples for the AI to learn from. And this is so important, especially for those very mild cases where they barely had any data to start with, right? Then you have the actual training, and right alongside it, constant validation. That's like giving the AI little pop quizzes on stuff it's never seen, just to make sure it's actually learning the concepts and not just memorizing the answers.
Now, this next part is a really fascinating look into how AI development actually works, because it's almost never a straight line. The team, right, they went ahead and built a bigger, more complex, more advanced model, and you know what happened? It was terrible. Its performance was just awful. So they had to literally scrap it and go back to an older, simpler design that, it turns out, worked way better. It's just a perfect reminder that with AI, more complex definitely does not always mean better.
Okay. So after all that training, all that trial and error, going back to the drawing board, it's finally time, the moment of truth. Let's see how our AI did on its final exam, a batch of scans it has never, ever laid eyes on before.
And the final accuracy score is 61.72%. Now, what does that actually mean? Well, think about it. With 4 different categories, if you were just guessing randomly, you'd be right about 25% of the time. So 61% is, well, it's definitely learned something. It's not just guessing. But yeah, it's also a long, long way from the kind of near-perfect score you'd need for a tool in a real hospital, right?
And honestly, that single number is super misleading. You have to look at the breakdown to get the real story. Look here, it was actually pretty decent at spotting the mild cases. Not bad at all. But then you look at the very mild cases, and what's the score? 0. A big fat 0.
It didn't correctly identify a single one. And that takes us right back to square one, doesn't it? It's that imbalanced data problem, that rare bird problem, coming back to haunt us.
And this is such a critical lesson with any AI. You can't just look at that one big number at the top. It can hide these massive problems. You've got to dig deeper and figure out not just where the AI is good, but just as importantly, where it is completely, totally blind.
But this leads to an even bigger, maybe more important question. Even when the AI does get it right, how? How is it making that decision? Is it actually looking at the medically relevant stuff, or is it just, I don't know, getting lucky by focusing on something random? Well, to answer that question, we have to bring in a whole field called explainable AI, or XAI for short. And this stuff is incredible. These are basically tools that let us crack open that AI black box and finally see what's going on inside, to understand how it's thinking.
For this specific project, the team used a cool technique called Grad-CAM. And what it does is pretty straightforward. It overlays a heat map on top of the original MRI. It shows you exactly which pixels the AI was paying the most attention to. So those bright red hotspots, that's what the AI decided was the most important part of the image for making its prediction. It's like we're literally seeing through the AI's eyes.
And the results they got from this are just amazing. When the AI got a diagnosis right, the heat maps would light up in the exact parts of the brain that neurologists already know are impacted by Alzheimer's. I mean, it was looking at the right stuff. It was incredible. But when it got an answer wrong, the heat maps told a totally different story. It was focusing on completely random, irrelevant things, like the edge of the skull or even the dark, empty space around the brain.
And look, this is way more than just a cool visual. This is absolutely essential. Think about it. For a doctor to ever trust a recommendation from an AI, they have to know why it's making that call. This kind of explainability helps the developers find the flaws and fix them. It's crucial for patient safety, and ultimately, it's the only way tools like this will ever get approved for use in the real world.
So let's circle back. Is this NeuroLens AI ready for prime time in hospitals tomorrow? Honestly, no. Not even close. But what this project does so perfectly is show us both the incredible, mind-blowing promise and the very real, tough challenges of AI in medicine. It reminds us that even though the tech isn't perfect, it's giving us a brand new lens to look at a disease that desperately needs one. Which really leaves us with the big question, doesn't it? What's the biggest hurdle we need to overcome for AI in medicine? Is it the technology itself? Is it getting the right data? Or is it really about us learning to trust the machine?